1.1 Importance of Chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain, and operation of a computer, production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new material. Chemistry contributes in a big way to the national economy. It also plays an important role in meeting human needs for food, healthcare products, and other material aimed at improving the quality of life. This is exemplified by the large scale production of a variety of fertilizers, improved variety of pesticides and insecticides. Chemistry provides methods for the isolation of life saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug AZT, azidothymidine, is used for helping AIDS patients. Chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new material having specific magnetic, electric, and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymers, metals, etc. These industries contribute in a big way to the economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants like CFCs, chlorofluorocarbons, responsible for ozone depletion in the stratosphere, have been successfully synthesized. However, many big environmental problems continue to be matters of grave concern to the chemist. One such problem is the management of greenhouse gases like methane, carbon dioxide, etc. Understanding of biochemical processes, use of enzymes for large scale production of chemicals, and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2 Nature of matter. You're already familiar with the term matter from your earlier classes. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of the states of matter which you learned in your previous classes. 1.2.1 States of matter. You are aware that matter can exist in three physical states, namely solid, liquid, and gas. The constituent particles of matter in these three states can be represented as shown in Figure 1.1. Particles are held very close to each other in solids in an orderly fashion and there is not much freedom of movement. In liquids, the particles are close to each other, but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid states, and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristics. 1. Solids have definite volume and definite shape. 2. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. 3. Gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. Solid with heat becomes liquid, which with heat becomes gas. Gas, when cooled, becomes liquid, which when cooled becomes solid. On heating, a solid usually changes to a liquid, and the liquid on further heating changes to gas or vapor. In the reverse process, a gas on cooling liquefies to the liquid, and the liquid on further cooling freezes to the solid. 1.2.2 Classification of matter. In Class 9, Chapter 2, you have learned that at the macroscopic or bulk level, matter can be classified as mixture or pure substance. These can be further subdivided as shown in Figure 1.2. When all constituent particles of a substance are same in chemical nature, it is said to be a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substances which may be present in it in any ratio. Hence, their composition is variable. Pure substances forming mixture are called its components. Many of the substances present around you are mixtures. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout the bulk of the mixture and its composition is uniform throughout. Sugar solution and air are the examples of homogeneous mixtures. In contrast to this, in a heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixtures of salt and sugar, grains and pulses, along with some dirt, often stone pieces, are heterogeneous mixtures. You can think of many more examples of mixtures which you come across in the daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods such as simple hand picking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixture. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water, and glucose are some examples of pure substances. Glucose contains carbon, hydrogen, and oxygen in a fixed ratio, and its particles are of the same composition. Hence, like all pure substances, glucose has a fixed composition. Also, its constituents, carbon, hydrogen, and oxygen, cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules from the previous classes. However, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. They all atoms are of one type. However, the atoms of different elements are different in nature. Some elements, such as sodium or copper, contain atoms as their constituent particles, whereas in some others, the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen, and oxygen gases consist of molecules in which two atoms combine to give their respective molecules. This is illustrated in Figure 1.3. When two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, the constituents of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Examples of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in Figure 1.4. Note that a water molecule comprises two hydrogen atoms and one oxygen atom. Similarly, a molecule of carbon dioxide contains two oxygen atoms combined with one carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compound formed by their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combustion, but water is used as a fire extinguisher. 1.3 Properties of matter and their measurement. 1.3.1 Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with acids and bases, etc. Physical properties can be measured or observed without changing the identity or composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The examples of chemical properties are characteristic reactions of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. 1.3.2 Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter, such as length, area, volume, etc., are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 m. Here, 6 is the number and m denotes meter. the unit in which length is measured. Earlier, two different systems of measurement, that is, the English system and the metric system, were being used in different parts of the world. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Later, need of a common standard was felt by the scientific community. Such a system was established in 1960 and is discussed in detail below. Maintaining the national standards of measurement. The system of units, including unit definitions, keeps on changing with time. Whenever the accuracy of measurement of a particular unit was enhanced substantially by adopting new principles, member nations of Meter Treaty, signed in 1875, agreed to change the formal definition of that unit. Each modern industrialized country, including India, has a Natural Metrology Institute (NMI) which maintains standards of measurements. This responsibility has been given to the National Physical Laboratory (NPL), New Delhi. This laboratory establishes experiments to realize the base units and derived units of measurement and maintains national standards of measurement. These standards are periodically intercompared with standards maintained at other national metrology institutes in the world, as well as those established at the International Bureau of Standards in Paris. 1.3.3 The International System of Units (SI). The International System of Units, in French, Le Système International de Units, abbreviated as SI, was established by the 11th General Conference on Weights and Measures (CGPM) from Conference General des Poids et Mesures. The CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. The SI system has 7 base units and they are listed in Table 1.1. These units pertain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc., can be derived from these quantities. The definitions of the SI base units are given in Table 1.2. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. These prefixes are listed in Table 1.3. Let us now quickly go through some of the quantities which you will be often using in this book. 1.3.4 Mass and Weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. You should be careful in using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. Figure 1.5. The SI unit of mass as given in Table 1.1 is kilogram. However, its fraction, named as gram, 1 kilo is equal to 1000 grams, is used in laboratories due to the smaller amounts of chemicals used in chemical reactions. 1.3.5 Volume. Volume is the amount of space occupied by a substance. It has the units of length raised to 3. So, in SI system, volume has units of meter cube. But again, in chemistry laboratories, smaller volumes are used. Hence, volume is often denoted in centimeter cube or dm cube units. A common unit, liter, L, which is not an SI unit is used for measurement of volume of liquids. 1 L is equal to 1000 ml. 1000 centimeter cube is equal to 1 dm cube. Figure 1.6 helps to visualize these relations. In the laboratory, the volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of a solution. These measuring devices are shown in Figure 1.7. 1.3.6 Density. The two properties, mass and volume, discussed above are related as follows. Density is equal to mass divided by volume. Density of a substance is its amount of mass per unit volume. So SI units of density can be obtained as follows. SI unit of density is equal to SI unit of mass divided by SI unit of volume, which is equal to kilogram divided by meter cube or kg m raised to minus 3. This unit is quite large and a chemist often expresses density in gram per centimeter cube, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. 1.3.7 Temperature. There are three common scales to measure temperature: degree Celsius, degree Fahrenheit, and K, Kelvin. Here, K is the SI unit. The thermometers based on these scales are shown in Figure 1.8. Generally, the thermometer with Celsius scale are calibrated from 0 degrees to 100 degrees, where these two temperatures are the freezing point and the boiling point of water respectively. The Fahrenheit scale is represented between 32 degree and 212 degree. The temperatures on two scales are related to each other by the following relationship. Degree Fahrenheit is equal to 9 divided by 5 degree Celsius plus 32. The Kelvin scale is related to Celsius scale as follows. K is equal to degree Celsius plus 273.15. It is interesting to note that temperature below 0 degree Celsius, that is, negative values, are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. 1.4 Uncertainty in measurement. Many a time in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently and present the data realistically with certainty to the extent possible. These ideas are discussed below in detail. Reference standard. After defining a unit of measurement such as the kilogram or the meter, scientists agreed on reference standards that make it possible to calibrate all measuring devices. For getting reliable measurements, all devices such as meter sticks and analytical balances have been calibrated by their manufacturers to give correct readings. However, each of these devices is standardized or calibrated against some reference. The mass standard is the kilogram since 1889. It has been defined as the mass of platinum iridium (PTIR) cylinder that is stored in an airtight jar at International Bureau of Weights and Measures in Sèvres, France. PTIR was chosen for this standard because it's highly resistant to chemical attack and its mass will not change for an extremely long time. Scientists are in search of a new standard for mass. This is being attempted through accurate determination of Avogadro constant. Work on this new standard focuses on ways to measure accurately the number of atoms in a well-defined mass of sample. One such method, which uses X-rays to determine the atomic density of a crystal of ultra-pure silicon, has an accuracy of about 1 part in 10 raised to 6, but has not yet been adopted to serve as a standard. There are other methods, but none of them are presently adequate to replace the PTIR cylinder. No doubt, changes are expected within this decade. The meter was originally defined as the length between two marks on a PTIR bar kept at a temperature of 0 degrees Celsius, 273.15 K. In 1960, the length of the meter was defined as 1.65076373 into 10 raised to 6 times the wavelength of light emitted by a krypton laser. Although this is a cumbersome number, it preserved the length of the meter at its agreed value. The meter was redefined in 1983 by CGPM as the length of path traveled by light in vacuum during a time interval of 1 by 299,792,458 of a second. Similar to the length and the mass, there are reference standards for other physical quantities. 1.4.1 Scientific Notation. As chemistry is the study of atoms and molecules which have extremely low masses and are present in extremely large numbers, a chemist has to deal with numbers as large as 6022 followed by 20 zeros for the molecules of 2 grams of hydrogen gas, or as small as 0.2300166 grams mass of a H atom. Similarly, other constants such as Planck's constant, speed of light, charges on particles, etc., involve numbers of the above magnitude. It may look funny for a moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication, or division with such numbers. You can write any two numbers of the above type and try any one of the operations you like to accept as a challenge, and then you will really appreciate the difficulty in handling such numbers. This problem is solved by using scientific notation for such numbers, that is, exponential notation, in which any number can be represented in the form capital N into 10 raised to small n, where small n is an exponent having positive or negative values, and capital N is a number called digit term which varies between 1.000 etc. and 9.999 etc. Thus, we can write 232.508 as 2.32508 into 10 raised to 2 in scientific notation. Note that while writing it, the decimal had to be moved to the left by 2 places, and the same is the exponent 2 of 10 in the scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 raised to minus 4. Here the decimal has to be moved 4 places to the right, and minus 4 is the exponent in the scientific notation. While performing mathematical operations on numbers expressed in scientific notations, the following points are to be kept in mind. Multiplication and division. These two operations follow the same rules which are there for exponential numbers. That is, 5.6 into 10 raised to 5 into 6.9 into 10 raised to 8 equals 5.6 into 6.9 into 10 raised to 5 plus 8 equals 5.6 into 6.9 into 10 raised to 13 equals 38.64 into 10 raised to 13 equals 3.864 into 10 raised to 14. 9.8 into 10 raised to minus 2 into 2.5 into 10 raised to minus 6 equals 9.8 into 2.5 into 10 raised to minus 2 plus minus 6 equals 9.8 into 2.5 into 10 raised to minus 2 minus 6 equals 24.50 into 10 raised to minus 8 equals 2.450 into 10 raised to minus 7. 2.7 into 10 raised to minus 3 divided by 5.5 into 10 raised to 4 equals 2.7 divided by 5.5 into 10 raised to minus 3 minus 4 equals 0.4909 into 10 raised to minus 7 equals 4.909 into 10 raised to minus 8. Addition and subtraction. For these two operations, first, the numbers are written in such a way that they have the same exponent. After that, the coefficients, digit terms, are added or subtracted as the case may be. Thus, For adding 6.65 into 10 raised to 4 and 8.95 into 10 raised to 3, exponent is made same for both the numbers. Thus we get 6.65 into 10 raised to 4 plus 0.895 into 10 raised to 4. Then these numbers can be added as follows: 6.65 plus 0.895 into 10 raised to 4 equals 7.545 into 10 raised to 4. Similarly, the subtraction of two numbers can be done as shown below. 2.5 into 10 raised to minus 2 minus 4.8 into 10 raised to minus 3 equals 2.5 into 10 raised to minus 2 minus 0.48 into 10 raised to minus 2 equals 2.5 minus 0.48 into 10 raised to minus 2 equals 2.02 into 10 raised to minus 2. 1.4.2 Significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using a platform balance and it comes out to be 9.4 grams. On measuring the mass of this object on an analytical balance, the mass obtained is 9.4213 grams. The mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. Therefore, digit 4 placed after decimal in the measurement by platform balance is uncertain. The uncertainty in the experimental or the calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus 1 which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Thus, if we write a result as 11.2 ml, we say the 11 is certain and 2 is uncertain, and the uncertainty would be plus or minus 1 in the last digit. Unless otherwise stated, an uncertainty of plus or minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. 1. All non-zero digits are significant. For example, in 285 centimeter, there are 3 significant figures, and in 0.25 ml, there are 2 significant figures. 2. Zeros preceding to first non-zero digit are not significant. Such zero indicates the position of decimal point. Thus, 0.03 has one significant figure and 0.0052 has two significant figures. 3. Zeros between two non-zero digits are significant. Thus, 2.005 has four significant figures. 4. Zeros at the end or right of a number are significant provided they are on the right side of the decimal point. For example, 0.200 grams has three significant figures, but if otherwise, the terminal zeros are not significant if there is no decimal point. For example, 100 has only one significant figure, but 100 has three significant figures and 100.0 has four significant figures. Such numbers are better represented in scientific notation. We can express the number 100 as 1 into 10 raised to 2 for one significant figure. 1.0 into 10 raised to 2 has two significant figures, and 1.00 into 10 raised to 2 has three significant figures. 5. Counting the numbers of objects, for example, 2 balls or 20 eggs, have infinite significant figures as these are exact numbers and can be represented by writing infinite number of zeros after placing a decimal. That is, 2 is equal to 2.000000 or 20 is equal to 20.000000. In numbers written in scientific notation, all digits are significant. Example, 4.01 into 10 raised to 2 has 3 significant figures, and 8.256 into 10 raised to minus 3 has 4 significant figures. However, one would always like the results to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurements for the same quantity. However, accuracy is the agreement of a particular value to the true value of the result. For example, if the true value for a result is 2.00 gram and student A takes two measurements and reports the results as 1.95 grams and 1.93 grams, these values are precise as they are close to each other but are not accurate. Another student B repeats the experiment and obtains 1.94 grams and 2.05 grams as the results for two measurements. These observations are neither precise nor accurate. When the third student C repeats these measurements and reports 2.01 grams and 1.99 grams as the result, these values are both precise and accurate. This can be more clearly understood from the data given in Table 1.4. Addition and subtraction of significant figures. The result cannot have more digits to the right of the decimal point than either of the original numbers. 12.11, 18.0, 1.012 equals 31.122. Here, 18.0 has only one digit after the decimal point, and the result should be reported only up to one digit after the decimal point, which is 31.1. Multiplication and division of significant figures. In these operations, the result must be reported with no more significant figures as in the measurement with the few significant figures. 2.5 into 1.25 equals 3.125. Since 2.5 has two significant figures, the result should not have more than two significant figures, thus it is 3.1. While limiting the result to the required number of significant figures as done in the above mathematical operation, one has to keep in mind the following points for rounding off the numbers. 1. If the rightmost digit to be removed is more than 5, the preceding number is increased by 1. For example, 1.386. If we have to remove 6, we have to round it to 1.39. 2. If the rightmost digit to be removed is less than 5, the preceding number is not changed. For example, 4.334. If 4 is to be removed, then the result is rounded up to 4.33. 3. If the rightmost digit to be removed is 5, then the preceding number is not changed if it is an even number, but it is increased by 1 if it is an odd number. For example, if 6.35 is to be rounded by removing 5, we have to increase 3 to 4, giving 6.4 as the result. However, if 6.25 is to be rounded off, it is rounded off to 6.2. 1.4.3 Dimensional analysis. Often, while calculating, there is a need to convert units from one system to the other. The method used to accomplish this is called factor label method or unit factor method or dimensional analysis. This is illustrated below. Example: a piece of metal is 3 inch long, represented by IN. What is its length in centimeter? Solution. We know that 1 inch equals 2.54 centimeter. From this equivalence, we can write 1 inch divided by 2.54 centimeter equals 1 equals 2.54 centimeter divided by 1 inch. Thus, 1 inch divided by 2.54 centimeter equals 1 and 2.54 centimeter divided by 1 inch also equals 1. Both of these are called unit factors. If some number is multiplied by these unit factors, that is 1, it will not be affected otherwise. Say, the 3 in given above is multiplied by the unit factor. So, 3 inch equals 3 inch into 2.54 centimeter divided by 1 inch equals 3 into 2.54 centimeter equals 7.62 centimeter. Now the unit factor by which multiplication is to be done is that unit factor 2.54 centimeter divided by 1 inch in the above case, which gives the desired units. That is, the numerator should have that part which is required in the desired result. It should also be noted in the above example that units can be handled just like other numerical part. It can be cancelled, divided, multiplied, squared, etc. Let's study one more example. Example: a jug contains 2 liters of milk. Calculate the volume of the milk in meter cube. Solution: since 1 liter is equal to 1000 centimeter cube and 1 meter is equal to 100 centimeter, which gives 1 meter by 100 centimeter equals 1, which is equal to 100 centimeter by 1 meter. To get meter cube from the above unit factors, the first unit factor is taken and it is cubed. 1 meter by 100 centimeter cube gives 1 meter cube by 10 raised to 6 centimeter cube, which is equal to 1 cube, which is equal to 1. Now, 2 liters is equal to 2 into 1000 centimeter cube. The above is multiplied by the unit factor 2 into 1000 centimeter cube into 1 meter cube by 10 raised to 6 centimeter cube, which is equal to 2 meter cube by 10 raised to 3, which is equal to 2 into 10 raised to minus 3 meter cube. Example: how many seconds are there in 2 days? Solution: here we know 1 day equals 24 hours h, or 1 day by 24h equals 1, which is equal to 24 hours by 1 day. Then 1h is equal to 60 minutes, or 1h by 60 minutes is equal to 1, which is equal to 60 minutes by 1 hour. So, for converting 2 days to seconds, that is 2 days equals blank 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 seconds. The unit factors can be multiplied in series in one step only as follows: 2 day into 24 hours by 1 day into 60 minutes divided by 1 hour into 60 seconds divided by 1 minute, which is equal to 2 into 24 into 60 seconds, which is equal to 172,800 seconds. 1.5 Laws of chemical combinations. The combination of elements to form compounds is governed by the following 5 basic laws. 1.5.1 Law of conservation of mass. This law was put forth by Anton Lavoisier in 1789. He performed careful experimental studies for combustion reactions and reached to the conclusion that in all physical and chemical changes, there is no net change in mass during the process. Hence, he reached the conclusion that matter can neither be created nor destroyed. This is called law of conservation of mass. This law formed the basis for several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactants and products, and carefully planned experiments performed by Lavoisier. 1.5.2 Law of Definite Proportions. This law was given by a French chemist, Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. Proust worked with two samples of cupric carbonate, one of which was of natural origin and the other was synthetic. He found that the composition of elements present in it was same for both the samples as shown below. Natural sample, percentage of copper 51.35, percentage of carbon 9.74, percentage of oxygen 38.91. Synthetic sample, percentage of copper 51.35, percentage of carbon 9.74, percentage of oxygen 38.91. Thus he concluded that irrespective of the source, a given compound always contains same elements combined together in the same proportion of mass. The validity of this law has been confirmed by various experiments. It is sometimes also referred to as law of definite composition. 1.5.3 Law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if two elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. For example, hydrogen combines with oxygen to form two compounds, namely water and hydrogen peroxide. 2 grams hydrogen plus 16 grams oxygen gives 18 grams water. 2 grams hydrogen plus 32 grams oxygen gives 34 grams hydrogen peroxide. Here, the masses of oxygen, that is 16 grams and 32 grams, which combined with a fixed mass of hydrogen 2 grams, bear a simple ratio, that is 16 is to 32 or 1 is to 2. 1.5.4 Gay-Lussac's Law of Gaseous Volumes. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Thus, 100 ml of hydrogen combined with 50 ml of oxygen to give 100 ml of water vapor. 100 ml hydrogen plus 50 ml oxygen gives 100 ml water. Thus, the volumes of hydrogen and oxygen which combine, that is 100 ml and 50 ml, bear a simple ratio of 2 is to 1. Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportions by volume. The law of definite proportions stated earlier was with respect to mass. The Gay-Lussac's law was explained properly by the work of Avogadro in 1811. 1.5.5 Avogadro's Law. In 1811, Avogadro proposed that equal volumes of all gases at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules, which is quite understandable in present times. If we consider again the reaction of hydrogen and oxygen to produce water, we see that two volumes of hydrogen combine with one volume of oxygen to give two volumes of water without leaving any unreacted oxygen. Note that in the figure 1.9, page 16, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic. If hydrogen and oxygen were considered as diatomic, as recognized now, then the above results are easily understandable. However, Dalton and others believed at that time that atoms of the same kind cannot combine, and molecules of oxygen and hydrogen containing two atoms did not exist. The proposal was published in the French Journal de Physique. In spite of being correct, it did not gain much support. After about 50 years in 1860, the first international conference on chemistry was held in Karlsruhe, Germany to resolve various ideas. At the meeting, Stanislaw Canizzario presented a sketch of a course of chemical philosophy which emphasized on the importance of Avogadro's work. 1.6 Dalton's atomic theory. Although the origin of the idea that matter is composed of small indivisible particles called atomio, meaning indivisible, dates back to the time of Democritus, a Greek philosopher 460 to 370 BC, it again started emerging as a result of several experimental studies which led to the laws mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following: 1. Matter consists of indivisible atoms. 2. All atoms of a given element have identical properties, including identical mass. Atoms of different elements differ in mass. 3. Compounds are formed when atoms of different elements combine in a fixed ratio. 4. Chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. Dalton's theory could explain the laws of chemical combination. However, it could not explain the laws of gaseous volumes. It could not provide the reason for combining of atoms, which was answered later by other scientists. 1.7 Atomic and molecular masses. After having some idea about the terms atoms and molecules, it's appropriate here to understand what do we mean by atomic and molecular masses. 1.7.1 Atomic mass. The atomic mass or the mass of an atom is actually very, very small because atoms are extremely small. Today, we have sophisticated techniques, example, mass spectrometry, for determining the atomic masses fairly accurately. But in the 19th century, scientists could determine the mass of one atom relative to another by experimental means, as has been mentioned earlier. Hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1 without any units, and other elements were assigned masses relative to it. However, the present system of atomic masses is based on carbon 12 as the standard and has been agreed upon in 1961. Here, carbon 12 is one of the isotopes of carbon and can be represented as 12C. In this system, 12C is assigned a mass of exactly 12 atomic mass unit AMU, and masses of all other atoms are given relative to this standard. One atomic mass unit is defined as a mass exactly equal to 1/12 of the mass of one carbon 12 atom, and 1 AMU equals 1.66056 into 10 raised to minus 24 grams. Mass of an atom of hydrogen equals 1.6736 into 10 raised to minus 24 grams. Thus, in terms of AMU, the mass of hydrogen atom equals 1.6736 into 10 raised to minus 24 grams divided by 1.66056 into 10 raised to minus 24 grams equals 1.0078 AMU equals 1.0080 AMU. Similarly, the mass of oxygen 16O atom would be 15.995 AMU. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculations, we actually use average atomic masses of elements, which are explained below. 1.7.2 Average atomic mass. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, percent occurrence, the average atomic mass of that element can be computed. For example, carbon has the following three isotopes with relative abundances and masses as shown against each of them. Isotope 12C, relative abundance 98.892%, atomic mass 12 AMU. Isotope 13C, relative abundance 1.108%, atomic mass 13.00335 AMU. Isotope 14C, relative abundance 2 into 10 raised to minus 10%, atomic mass 14.00317. From the above data, the average atomic mass of carbon will come out to be 0.98892 into 12U plus 0.01108 into 13.00335U plus 2 into 10 raised to minus 12 into 14.00317U equals 12.011U. Similarly, average atomic masses for other elements can be calculated. In the periodic table of elements, the atomic masses mentioned for different elements actually represent their average atomic masses. 1.7.3 Molecular mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. For example, molecular mass of methane, which contains one carbon atom and four hydrogen atoms, can be obtained as follows. Molecular mass of methane CH4 equals 12.011U plus 4 into 1.008U equals 16.043U. Similarly, molecular mass of water H2O equals 2 into atomic mass of hydrogen plus 1 into atomic mass of oxygen equals 2 into 1.008U plus 16U equals 18.02U. 1.7.4 Formula mass. Some substances such as sodium chloride do not contain discrete molecules as their constituent units. In such compounds, positive sodium ion and negative chloride ion entities are shown in a three-dimensional structure as shown in figure 1.10. It may be noted that in sodium chloride, one Na plus ion is surrounded by 6 Cl minus ion and vice versa. The formula such as NaCl is used to calculate the formula mass instead of molecular mass, as in the solid state sodium chloride does not exist as a single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine equals 23.0 U plus 35.5 U equals 58.5 U. Problem 1.1. Calculate the molecular mass of glucose C6H12O6 molecule. Solution. Molecular mass of glucose C6H12O6 equals 6 into 12.011 U plus 12 into 1.008 U plus 6 into 16.00 U equals 72.066 U plus 12.096 U plus 96.00 U equals 180.162 U. 1.8. Mole concept and molar masses. Atoms and molecules are extremely small in size, and their numbers in even a small amount of any substance is really very large. To handle such large numbers, a unit of convenient magnitude is required. Just as we denote 1 dozen for 12 items, score for 20 items, gross for 144 items, we use the idea of mole to count entities at the microscopic level, that is, atoms, molecules, particles, electrons, ions, etc. In SI system, mole, symbol MOL, was introduced as seventh base quantity for the amount of a substance. The mole, symbol MOL, is the SI unit of amount of substance. 1 mole contains exactly 6.022 into 10 raised to 23 elementary entities. This number is the fixed numerical value of the Avogadro constant Na when expressed in the unit per mole, or is called the Avogadro number. The amount of substance, symbol small n, of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, any other particle or specified group of particles. It may be emphasized that the mole of a substance always contains the same number of entities no matter what the substance may be. In order to determine this number precisely, the mass of a carbon-12 atom was determined by a mass spectrometer and found to be equal to 1.992648 into 10 raised to minus 23 grams. Knowing that 1 mole of carbon weighs 12 grams, the number of atoms in it is equal to 12 grams per mole 12C divided by 1.992648 into 10 raised to minus 23 grams per 12C atom equals 6.0221367 into 10 raised to 23 atoms per mole. This number of entities in 1 mole is so important that it is given a separate name and symbol. It is known as Avogadro constant or Avogadro number, denoted by capital N, capital A, in honor of Amedeo Avogadro. To appreciate the largeness of this number, let us write it with all zeros without using any powers of 10. 60221367 followed by 16 zeros. Hence, so many entities, atoms, molecules, or any other particle constitute 1 mole of a particular substance. We can say therefore that 1 mole of hydrogen atoms is equal to 6.022 into 10 raised to 23 atoms. 1 mole of water molecules equals 6.022 into 10 raised to 23 water molecules. 1 mole of sodium chloride is equal to 6.022 into 10 raised to 23 formula units of sodium chloride. Having defined the mole, it is easier to know the mass of 1 mole of a substance or the constituent entities. The mass of 1 mole of a substance in grams is called its molar mass. The molar mass in grams is numerically equal to atomic or molecular or formula mass in U. Molar mass of water is equal to 18.02 grams per mole. Molar mass of sodium chloride is equal to 58.5 g per mole. 1.9 Percentage composition. So far, we were dealing with the number of entities present in a given sample. But many a time, information regarding the percentage of a particular element present in a compound is required. Suppose an unknown or new compound is given to you. The first question you would ask is, what is its formula? Or what are its constituents? And in what ratio are they present in the given compound? For known compounds also, such information provides a check whether the given sample contains the same percentage of elements as present in a pure sample. In other words, one can check the purity of a given sample by analyzing this data. Let's understand it by taking the example of water H2O. Since water contains hydrogen and oxygen, the percentage composition of both these elements can be calculated as follows. Mass percentage of an element is equal to mass of that element in the compound into 100 divided by molar mass of the compound. Molar mass of water is equal to 18.02 grams. Mass percentage of hydrogen is equal to 2 into 1.008 divided by 18.02 into 100 equals 11.18. Mass percentage of oxygen is equal to 16 divided by 18.02 into 100 equals 88.79. Let us take one more example. What is the percentage of carbon, hydrogen and oxygen in ethanol? Molecular formula of ethanol is C2H5OH. Molar mass of ethanol is 2 into 12.01 plus 6 into 1.008 plus 16.00 grams equals 46.068 grams. Mass percent of carbon equals 24.02 grams divided by 46.068 grams into 100 equals 52.14%. Mass percent of hydrogen equals 6.048 grams divided by 46.068 grams into 100 equals 13.13%. Mass percent of oxygen equals 16.00 grams divided by 46.068 grams into 100 equals 34.73%. After understanding the calculation of percent of mass, let us now see what information can be obtained from the percent composition data. 1.9.1 Empirical formula for molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of a compound. If the mass percent of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can further be obtained if the molar mass is known. The following example illustrates this sequence. Problem 1.2. A compound contains 4.07% hydrogen, 24.27% carbon, and 71.65% chlorine. Its molar mass is 98.96 grams. What are its empirical and molecular formulas? Solution. Step 1. Conversion of mass percent to grams. Since we are having mass percent, it's convenient to use 100 grams of the compound as the starting material. Thus, in 100-gram sample of the above compound, 4.07 grams hydrogen, 24.27 grams carbon, and 71.65 grams chlorine are present. Step 2. Convert into number moles of each element. Divide the masses obtained above by respective atomic masses of various elements. This gives the number of moles of constituent elements in the compound. Moles of hydrogen is equal to 4.07 grams by 1.008 grams equals 4.04. Moles of carbon equals 24.27 grams divided by 12.01 grams equals 2.021. Moles of chlorine is equal to 71.65 grams divided by 35.453 grams equals 2.021. Step 3. Divide each of the mole values obtained above by the smallest number amongst them. Since 2.021 is the smallest value, division by it gives a ratio of 2:1:1 for H:(C:)Cl. In case the ratios are not whole numbers, then they may be converted into whole number by multiplying by a suitable coefficient. Step 4. Write down the empirical formula by mentioning the numbers after writing the symbols of respective elements. CH2Cl is thus the empirical formula of the above compound. Step 5. Writing molecular formula. A. Determine empirical formula mass by adding the atomic masses of various atoms present in the empirical formula. For CH2Cl, empirical formula mass is 12.01 plus 2 into 1.008 plus 35.453 equals 49.48 grams. B. Divide molar mass by empirical formula mass. Molar mass divided by empirical formula mass equals 98.96 grams divided by 49.48 grams equals 2 equals small n. C. Multiply empirical formula by small n obtained above to get the molecular formula. Empirical formula equals CH2Cl, N is equal to 2. Hence, molecular formula is C2H4Cl2. 1.10 Stoichiometry and stoichiometric calculations. The word stoichiometry is derived from two Greek words, stoichion meaning element and metron meaning measure. Stoichiometry thus deals with the calculation of masses, sometimes volumes also, of the reactants and the products involved in a chemical reaction. Before understanding how to calculate the amounts of reactants required or the products produced in a chemical reaction, let us study what information is available from the balanced chemical equation of a given reaction. Let us consider the combustion of methane. A balanced equation for this reaction is as given below. CH4G plus 2O2G gives CO2G plus 2H2OG. Here, methane and dioxygen are called reactants and carbon dioxide and water are called products. Note that all the reactants and the products are gases in the above reaction and this has been indicated by the letter G in the brackets next to its formula. Similarly, in case of solids and liquids, S and L are written respectively. The coefficients 2 for O2 and H2O are called stoichiometric coefficients. Similarly, the coefficient for CH4 and CO2 is 1 in each case. They represent the number of molecules and moles as well taking part in the reaction or formed in the reaction. Thus, according to the above chemical reaction, 1 mole of CH4 gas reacts with 2 moles of O2 gas to give 1 mole of CO2 gas and 2 moles of H2O gas. 1 molecule of CH4 gas reacts with 2 molecules of O2 gas to give 1 molecule of CO2 gas and 2 molecules of H2O gas. 22.7 L of CH4 gas reacts with 45.4 L of O2 gas to give 22.7 L of CO2 gas and 45.4 L of H2O gas. 16 grams of CH4 gas reacts with 2 into 32 grams of O2 gas to give 44 grams of CO2 gas and 2 into 18 grams of H2O gas. From these relationships, the given data can be interconverted as follows. Mass gives moles gives number of molecules. Mass divided by volume equals density. 1.10.1 Limiting reagent. Many a time, reactions are carried out with the amounts of reactants that are different than the amounts as required by a balanced chemical reaction. In such situations, one reactant is in more amount than the amount required by balanced chemical reaction. The reactant which is present in the least amount gets consumed after some time, and after that, further reaction does not take place whatever be the amount of the other reactant. Hence, the reactant which gets consumed first limits the amount of product formed and is therefore called the limiting reagent. In performing stoichiometric calculations, this aspect is also to be kept in mind. Balancing a chemical equation. According to the law of conservation of mass, a balanced chemical equation has the same number of atoms of each element on both sides of the equation. Many chemical equations can be balanced by trial and error. Let us take the reactions of a few metals and non-metals with oxygen to give oxides. 4Fe solid plus 3O2 gas gives 2Fe2O3 solid. A. Balanced equation. 2Mg solid plus O2 gas gives 2MgO solid. B. Balanced equation. P4 solid plus O2 gas gives P4O10 solid. C. Unbalanced equation. Equations A and B are balanced since there are same number of metal and oxygen atoms on each side of the equations. However, equation C is not balanced. In this equation, phosphorus atoms are balanced but not the oxygen atoms. To balance it, we must place the coefficient 5 on the left of oxygen on the left side of the equation to balance the oxygen atoms appearing on the right side of the equation. P4 solid plus 5O2 gas gives P4O10 solid, balanced equation. Now let us take the combustion of propane C3H8. This equation can be balanced in steps. Step 1. Write down the correct formulas of reactants and products. Here, propane and oxygen are reactants and carbon dioxide and water are products. C3H8 gas plus O2 gas gives CO2 gas plus H2O liquid. Unbalanced equation. Step 2. Balance the number of C atoms. Since 3 carbon atoms are in the reactant, therefore 3 CO2 molecules are required on the right side. C3H8 gas plus O2 gas gives 3 CO2 gas plus H2O liquid. Step 3. Balance the number of H atoms. On the left, there are 8 hydrogen atoms in the reactants. However, each molecule of water has 2 hydrogen atoms, so 4 molecules of water will be required for 8 hydrogen atoms on the right side. C3H8 gas plus O2 gas gives 3 CO2 gas plus 4 H2O liquid. Step 4. Balance the number of O atoms. There are 10 oxygen atoms on the right side. 3 into 2 equals 6 in CO2 and 4 into 1, 4 in water. Therefore, 5 O2 molecules are needed to supply the required 10 CO2 and 4 into 1, 4 in water. Therefore, 5 O2 molecules are needed to supply the required 10 oxygen atoms. C3H8 gas plus 5O2 gas gives 3 CO2 gas plus 4 H2O liquid. Step 5. Verify that the number of atoms of each element is balanced in the final equation. The equation shows 3 carbon atoms, 8 hydrogen atoms, and 10 oxygen atoms on each side. All equations that have correct formulas for all reactants and products can be balanced. Always remember that subscripts in formulas of reactants and products cannot be changed to balance an equation. Problem 1.3. Calculate the amount of water gas produced by the combustion of 16 g of methane. Solution. The balanced equation for the combustion of methane is CH4G plus 2O2G gives CO2G plus 2H2OG. 1. 16G of CH4 corresponds to 1 mole. 2. From the above equation, 1 mole of CH4G gives 2 mole of H2OG. 2 moles of water H2O equals 2 into 2 plus 16 equals 2 into 18 equals 36G. 1 mole H2O equals 18G H2O gives 18G H2O divided by 1 mole H2O equals 1. Hence, 2 mole H2O into 18G H2O divided by 1 mole H2O equals 2 into 18G H2O equals 36G H2O. Problem 1.4. How many moles of methane are required to produce 22G CO2G after combustion? Solution. According to the chemical equation, CH4G plus 2O2G gives CO2G plus 2H2OG. 44G CO2 is obtained from 16G CH4. Therefore, 1 mole CO2 is obtained from 1 mole of CH4 gas. Number of moles of CO2 equals 22G CO2 gas into 1 mole CO2 gas divided by 44G CO2 gas equals 0.5 mole CO2 gas. Hence, 0.5 mole CO2G would be obtained from 0.5 mole CH4G, or 0.5 mole of CH4 gas would be required to produce 22G CO2 gas. Problem 1.5. 50 kg of N2 gas and 10 kg of H2 gas are mixed to produce NH3 gas. Calculate the amount of NH3 gas formed. Identify the limiting reagent in the production of NH3 in this situation. Solution. A balanced equation for the above reaction is written as follows. N2 gas plus 3H2 gas gives 2NH3 gas. Calculation of moles. Number of moles of N2 equals 50 kg N2 multiplied by 1000 grams N2 divided by 1 kg N2 multiplied by 1 mole N2 divided by 28 grams N2 equals 17.86 multiplied by 10 raised to 2 moles. Number of moles of H2 equals 10 kilo H2 multiplied by 1000 grams H2 divided by 1 kilogram H2 multiplied by 1 mole H2 divided by 2.016 gram H2 equals 4.96 multiplied by 10 raised to 3 moles. According to the above equation, 1 mole N2 gas requires 3 mole H2 gas for the reaction. Hence, for 17.86 into 10 raised to 2 moles of N2, the moles of H2 gas required would be 17.86 into 10 raised to 2 moles N2 multiplied by 3 moles H2 gas divided by 1 mole N2 gas equals 5.36 into 10 raised to 3 moles H2. But we have only 4.96 into 10 raised to 3 moles H2. Hence, dihydrogen is the limiting reagent in this case. So, NH3 gas would be formed only from that amount of available dihydrogen, that is 4.96 into 10 raised to 3 moles. Since 3 moles H2 gas gives 2 moles NH3 gas, 4.96 into 10 raised to 3 moles H2 gas multiplied by 2 moles NH3 gas divided by 3 moles H2 gas equals 3.30 into 10 raised to 3 moles NH3 gas. 3.30 into 10 raised to 3 moles NH3 gas is obtained. If they are to be converted to grams, it is done as follows. 1 mole NH3 gas equals 17 gram NH3 gas. 3.30 into 10 raised to 3 moles NH3 gas multiplied by 17 grams NH3 gas divided by 1 mole NH3 gas equals 3.30 into 10 raised to 3 multiplied by 17 grams NH3 gas equals 56.1 multiplied by 10 raised to 3 grams NH3 equals 56.1 kilogram NH3. 1.10.2 Reactions in solutions. A majority of reactions in the laboratories are carried out in solutions. Therefore, it is important to understand as how the amount of substance is expressed when it is present in the solution. The concentration of a solution or the amount of substance present in its given volume can be expressed in any one of the following ways. 1. Mass percent or weight percent, W by W percentage. 2. Mole fraction. 3. Molarity. 4. Molality. Let us now study each one of them in detail. 1. Mass percent. It is obtained by using the following relation. Mass percent equals mass of solute divided by mass of solution into 100. Problem 1.6. A solution is prepared by adding 2g of a substance A to 18g of water. Calculate the mass percent of the solute. Solution. Mass percent of A equals mass of A divided by mass of solution into 100 equals 2g divided by 2g of A plus 18g of water into 100 equals 2g divided by 20g into 100 equals 10%. 2. Mole fraction. It is the ratio of number of moles of a particular component to the total number of moles in the solution. If a substance A dissolves in substance B and their number of moles are Na and Nb respectively, then the mole fractions of A and B are given as mole fraction of A equals number of moles of A divided by number of moles of solution equals Na divided by Na plus Nb. Mole fraction of B equals number of moles of B divided by number of moles of solution equals Nb divided by Na plus Nb. 3. Molarity. It is the most widely used unit and is denoted by capital M. It is defined as the number of moles of the solute in 1 liter of the solution. Thus, molarity M equals number of moles of solute divided by volume of solution in liters. Suppose we have 1 m solution of a substance, say NaOH, and we want to prepare a 0.2 m solution from it. 1 m NaOH means 1 mole of NaOH present in 1 liter of the solution. For 0.2 m solution, we require 0.2 moles of NaOH dissolved in 1 liter solution. Hence, for making 0.2 m solution from 1 m solution, we have to take that volume of 1 m NaOH solution, which contains 0.2 mole of NaOH, and dilute the solution with water to 1 liter. Now, how much volume of concentrated 1 m NaOH solution be taken, which contains 0.2 moles of NaOH, can be calculated as follows. If 1 mole is present in 1 liter or 1000 ml solution, then 0.2 mole is present in 1000 ml divided by 1 mole into 0.2 mole solution equals 200 ml solution. Thus, 200 ml of 1m NaOH are taken and enough water is added to dilute it to make it 1 liter. In fact, for such calculations, a general formula M1 into V1 equals M2 into V2, where capital M and V are molarity and volume respectively, can be used. In this case, M1 is equal to 0.2 capital M, V1 equals 1000 ml, and capital M2 equals 1.0 capital M. V2 is to be calculated. Substituting the values in the formula, 0.2 capital M into 1000 ml equals 1 capital M into V2. V2 is equal to 0.2 capital M into 1000 ml divided by 1.0 capital M equals 200 liters. Note that the number of moles of solute NaOH was 0.2 in 200 ml and it has remained the same, that is 0.2 even after dilution in 1000 ml, as we have changed just the amount of solvent, that is water, and have not done anything with respect to NaOH. But keep in mind the concentration. Problem 1.7. Calculate the molarity of NaOH in the solution prepared by dissolving its 4G in enough water to form 250 ml of the solution. Solution. Since molarity capital M is equal to number of moles of solute divided by volume of solution in liters, it's equal to mass of NaOH by molar mass of NaOH divided by 0.250 liters equals 4G by 40G divided by 0.250 liters equals 0.1 mole divided by 0.250 liters equals 0.4 per mole or 0.4 m, capital M. Note that the molarity of a solution depends upon temperature because volume of a solution is temperature dependent. 4. Molality. It is defined as the number of moles of solute present in 1 kilogram of solvent. It is denoted by small m. Thus, molality small m is equal to number of moles of solute divided by mass of solvent in kilogram. Problem 1.8. The density of 3 capital M solution of NaCl is 1.25 grams per milliliter. Calculate the molality of the solution. Solution. Capital M is equal to 3 moles per liter. Mass of NaCl in 1 liter solution is equal to 3 into 58.5 equals 175.5 grams. Mass of 1 liter solution is equal to 1000 into 1.25 equals 1250 grams, since density is equal to 1.25 grams per milliliter. Mass of water in solution is equal to 1250 minus 75.5 equals 1074.5 grams. Molality is equal to number of moles of solute divided by mass of solvent in kilogram equals 3 moles divided by 1.0745 kilogram equals 2.79 m, small m. Often in a chemistry laboratory, a solution of a desired concentration is prepared by diluting a solution of known higher concentration. The solution of higher concentration is also known as stock solution. Note that the molality of a solution does not change with temperature since mass remains unaffected with temperature. Summary. Chemistry, as we understand it today, is not a very old discipline. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied the knowledge in various walks of life. The study of chemistry is very important as its domain encompasses every sphere of life. Chemists study the properties and structure of substances and the changes undergone by them. All substances contain matter, which can exist in three states: solid, liquid, or gas. The constituent particles are held in different ways in these states of matter and they exhibit their characteristic properties. Matter can also be classified into elements, compounds, or mixtures. An element contains particles of only one type, which may be atoms or molecules. The compounds are formed where atoms of two or more elements combine in a fixed ratio to each other. Mixtures occur widely, and many of the substances present around us are mixtures. When the properties of a substance are studied, measurement is inherent. The quantification of properties requires a system of measurement and units in which the quantities are to be expressed. Many systems of measurement exist, of which the English and the metric systems are widely used. The scientific community, however, has agreed to have a uniform and common system throughout the world, which is abbreviated as SI units, International System of Units. Since measurements involve recording of data, which are always associated with a certain amount of uncertainty, the proper handling of data obtained by measuring the quantities is very important. The measurements of quantities in chemistry are spread over a wide range of 10 raised to minus 31 to 10 raised to plus 23. Hence, a convenient system of expressing the numbers in scientific notation is used. The uncertainty is taken care of by specifying the number of significant figures in which the observations are reported. The dimensional analysis helps to express the measured quantities in different systems of units. Hence, it is possible to interconvert the results from one system of units to another. The combination of different atoms is governed by basic laws of chemical combination, these being the law of conservation of mass, law of definite proportions, law of multiple proportions, Gay-Lussac's law of gaseous volumes, and Avogadro law. All these laws led to the Dalton's atomic theory, which states that atoms are building blocks of matter. The atomic mass of an element is expressed relative to 12C isotope of carbon, which has an exact value of 12U. Usually, the atomic mass used for an element is the average atomic mass obtained by taking into account the natural abundance of different isotopes of that element. The molecular mass of a molecule is obtained by taking sum of the atomic masses of different atoms present in a molecule. The molecular formula can be calculated by determining the mass percent of different elements present in a compound and its molecular mass. The number of atoms, molecules, or any other particles present in a given system are expressed in the terms of Avogadro constant 6.022 into 10 raised to 23. This is known as 1 mole of the respective particles or entities. Chemical reactions represent the chemical changes undergone by different elements and compounds. A balanced chemical equation provides a lot of information. The coefficients indicate the molar ratios and the respective number of particles taking part in a particular reaction. The quantitative study of the reactants required or the products formed is called stoichiometry. Using stoichiometric calculations, the amount of one or more reactants required to produce a particular amount of product can be determined and vice versa. The amount of substance present in a given volume of a solution is expressed in a number of ways. Example, mass percent, mole fraction, molarity, and molality. Exercises 1.1. Calculate the molar mass of the following: 1. H2O, 2. CO2, 3. CH4. 1.2. Calculate the mass percent of different elements present in sodium sulfate Na2SO4. 1.3. Determine the empirical formula of an oxide of iron which has 69.9% iron and 30.1% dioxygen by mass. 1.4. Calculate the amount of carbon dioxide that could be produced when 1. 1 mole of carbon is burned in air. 2. 1 mole of carbon is burned in 16 grams of dioxygen. 3. 2 moles of carbon are burnt in 16 grams of dioxygen. 1.5. Calculate the mass of sodium acetate CH3COONA required to make 500 ml of 0.375 molar aqueous solution. Molar mass of sodium acetate is 82.0245 grams per mole. 1.6. Calculate the concentration of nitric acid in moles per liter in a sample which has a density 1.41 grams per milliliter and the mass percent of nitric acid in it being 69%. 1.7. How much copper can be obtained from 100 grams of copper sulfate CuSO4? 1.8. Determine the molecular formula of an oxide of iron in which the mass percent of iron and oxygen are 69.9 and 30.1 respectively. 1.9. Calculate the atomic mass average of chlorine using the following data: 35 Cl, percentage natural abundance 75.77, molar mass 34.9689, 37 Cl, percentage natural abundance 24.23, molar mass 36.9659. 1.10. In 3 moles of ethane C2H6, calculate the following: 1. Number of moles of carbon atoms. 2. Number of moles of hydrogen atoms. 3. Number of molecules of ethane. 1.11. What is the concentration of sugar C12H22O11 in mole per liter if its 20 grams are dissolved in enough water to make a final volume up to 2 liters? 1.12. If the density of methanol is 0.793 kg per liter, what is its volume needed for making 2.5 liters of its 0.25 capital M solution? 1.13. Pressure is determined as force per unit area of the surface. The SI unit of pressure Pascal is as shown below. 1 PA equals 1 capital N per meter squared. If mass of air at sea level is 1034 gram per centimeter squared, calculate the pressure in Pascal. 1.14. What is the SI unit of mass? How is it defined? 1.15. Match the following prefixes with its multiples. Prefixes: 1 micro, 2 deca, 3 mega, 4 giga, 5 femto. Multiples: 10 raised to 6, 10 raised to 9, 10 raised to minus 6, 10 raised to minus 15, 10. 1.16. What do you mean by significant figures? 1.17. A sample of drinking water was found to be severely contaminated with chloroform CHCl3, supposed to be carcinogenic in nature. The level of contamination was 15 ppm by mass. 1. Express this in percent by mass. 2. Determine the molality of chloroform in the water sample. 1.18. Express the following in the scientific notation. 1. 0.0048. 2. 234,000. 3. 8,008. 4. 500.0. 5. 6.0012. 1.19. How many significant figures are present in the following? 1. 0.0025. 2. 208. 3. 5005. 4. 126,000. 5. 500. 6. 2.0034. 1.2. Round up the following up to 3 significant figures. 1. 34.216. 2. 10.4107. 3. 0.04597. 4. 2808. 1.21. The following data are obtained when dinitrogen and dioxygen react together to form different compounds. Mass of dinitrogen 1. 14 grams. Mass of dioxygen 16 grams. 2. Mass of dinitrogen 14 grams. Mass of dioxygen 32 grams. 3. Mass of dinitrogen 28 grams. Mass of dioxygen 32 grams. 4. Mass of dinitrogen 28 grams. Mass of dioxygen 80 grams. A. Which law of chemical combination is obeyed by the above experimental data? Give its statement. B. Fill in the blanks in the following conversions. 1. 1 kilometer equals blank mm equals blank pm. 2. 1 mg equals blank kg equals blank ng. 3. 1 ml equals blank liters equals blank dm cube. 1.22. If the speed of light is 3.0 into 10 raised to 8 meter per second, calculate the distance covered by light in 2.00 ns. 1.23. In a reaction, A plus B2 gives AB2. Identify the limiting reagent, if any, in the following reaction mixtures. 1. 300 atoms of A plus 200 molecules of B. 2. 2 mole A plus 3 mole B. 3. 100 atoms of A plus 100 molecules of B. 4. 5 mole A plus 2.5 mole B. 5. 2.5 mole A plus 5 mole B. 1.24. Dinitrogen and dihydrogen react with each other to produce ammonia according to the following chemical equation. N2 gas plus H2 gas gives 2NH3 gas. 1. Calculate the mass of ammonia produced if 2 into 10 raised to 3 grams dinitrogen reacts with 1 into 10 raised to 3 grams of dihydrogen. 2. Will any of the two reactants remain unreacted? 3. If yes, which one and what would be its mass? 1.25. How are 0.50 mole Na2CO3 and 0.50 capital M Na2CO3 different? 1.26. If 10 volumes of dihydrogen gas reacts with 5 volumes of dioxygen gas, how many volumes of water vapor would be produced? 1.27. Convert the following into basic units. 1. 28.7 pm. 2. 15.15 pm. 3. 25,365 mg. 1.28. Which one of the following will have the largest number of atoms? 1. 1 gram Au solid. 2. 1 gram Na solid. 3. 1 gram Li solid. 4. 1 gram of Cl2 gas. 1.29. Calculate the molarity of a solution of ethanol in water in which the mole fraction of ethanol is 0.040. Assume the density of water to be 1. 1.30. What will be the mass of one 12C atom in G? 1.31. How many significant figures should be present in the answer of the following calculations? 1. 0.02856 into 298.15 into 0.112 divided by 0.5785. 2. 5 into 5.364. 3. 0.0125 plus 0.7864 plus 0.0215. 1.32. Use the data given in the following table to calculate the molar mass of naturally occurring argon isotope. Isotope 36Ar, isotopic molar mass 35.96755 grams per mole. Abundance 0.337%. Isotope 38Ar, isotopic molar mass 37.96272 grams per mole. Abundance 0.063%. Isotope 40Ar, isotopic molar mass 39.9624 grams per mole. Abundance 99.600%. 1.33. Calculate the number of atoms in each of the following. 1. 52 moles of Ar. 2. 52 U of He. 3. 52 grams of He. 1.34. A welding fuel gas contains carbon and hydrogen only. Burning a small sample of it in oxygen gives 3.38 grams carbon dioxide, 0.690 grams of water, and no other products. A volume of 10 liters measured at STP of this welding gas is found to weigh 11.6 grams. Calculate 1. Empirical formula, 2. Molar mass of the gas, and 3. Molecular formula. 1.35. Calcium carbonate reacts with aqueous HCl to give CaCl2 and CO2. According to the reaction, CaCO3 solid plus 2HClAq gives CaCl2Aq plus CO2 gas plus H2O liquid. What mass of CaCO3 is required to react completely with 25 ml of 0.75 capital M HCl? 1.36. Chlorine is prepared in the laboratory by treating manganese dioxide MnO2 with aqueous hydrochloric acid. According to the reaction, 4HClAq plus MnO2 solid gives 2H2O liquid plus MnCl2Aq plus Cl2 gas. How many grams of HCl react with 5 grams of manganese dioxide?